This topic is about Lab 3. Lab 3 will be analysis of first order systems. So in preparing to Lab 3, you need to read about some MATLAB functions like LSIM. That means it is used for linear system simulation, impulse function, a step function in MATLAB. You just go to MATLAB and access help, and then from there you can search LSIM, impulse and step functions, and study what these functions are used when we work with MATLAB. Lab report 3, of course, as usual, it includes theoretical analysis of solving first order system, a system described by first order differential equation, and your MATLAB simulation results, including figures, and comparing your theoretical mathematical analysis with the MATLAB simulation and discussions of the results. Okay, as an example, let's solve this first order differential equation. This is, as you know, we already studied in the ECEN221 lecture class. This is first order differential equation. Why? Because here the maximum derivative is first derivative. It relates, remember, a differential equation relates the input and the output. In this case, x of t is the input to the system, and y of t is the output of the system. And this differential equation is dy by dt plus 2 times y of t is equal to xt. So the maximum derivative for the output is first derivative. So that's why it is called first order differential equation, relating the input x of t and the output y of t. Now in the theoretical work, what you should do, you need to find the impulse response and the step response of the system. Okay, this is the first order system. Find the impulse response and the step response of the system. How you find the impulse and the step response? Here is, I have some hints how to do it. First, you find the step response. What is the step response of the system? The step response of the system means the response of the system when the input is unit step function. So you give x of t is equal to u of t. And then because it's first order differential equation, to get the output yt, you need the input and the initial condition. The initial condition is y at 0 is equal to 0. This is usually when we try to find the impulse response, we assume the initial condition is 0. Okay, so by giving the input x of t, u of t, and using initial condition y at 0 is equal to 0, you'll get the output, the complete solution for y of t. Y of t will have homogeneous solution and particular solution, as you know, and the complete solution will be the homogeneous solution plus the particular solution. And considering the input, the initial condition 0, you will find a complete solution. That complete solution is the step response of the system. Why? Because our input is x of t is equal to ut, the unit step function. From the step response, we can find the impulse response. What is the relation between the step response and the impulse response? If you remember, the relation between the unit step and u of t and the unit impulse function Dirac t. Dirac t is the derivative of u of t. So unit step function is the derivative of unit impulse function is the derivative of unit step function. By that analogy, the impulse response will be the derivative of the step response. Okay, so you will find the complete solution considering x of t is equal to ut and initial condition 0. That will be the step response. You differentiate, or you find the derivative of the output with respect to time. That will be the impulse response of the system. So you need to get S of t and h of t. S of t is the step response of the system, and h of t is the impulse response of the system. This is part A of the theoretical work. Another theoretical work is you will find the output of this system considering x of t is equal to e to the power of minus 5t ut. In this case, different input. So for this input, again, assuming initial condition 0, you'll find the output yt. So you have to do part A and part B paperwork, theoretical mathematical analysis. Now, these two works, we need it for the MATLAB simulation, okay? The MATLAB simulation of part A will be determining the impulse and step response of the same system, this system. However, we will do it using MATLAB simulation results using the impulse and step functions. Okay, using the impulse and step functions. So this is I just gave a sample code here how we find the impulse and step response. So to find the impulse and step response, first we need to find the coefficients A's and B's. The A's are the coefficient for y of t, as you remember from the differential equation, and the B's are the coefficient for x of t. Here, for x of t, I have B0 only. B0 is the coefficient of x, which is 1. For the case of the A's, the A0 will be 2, the coefficient of y of t, and A1 will be the coefficient of dy by dt, the first derivative. Okay, so by this way, we will make the A vector. The A vector consisting of all S, which are the coefficients of the derivative of y. It can be second derivative, a first derivative, and no derivative, depending on the order of the system. For the first order, only we have first derivative. So the coefficient of the first derivative of y is 1, the coefficient of y of t is 2, then we make a vector A is equal to 1, 2. So always you put the vector in descending order from the highest derivative to the lowest derivative. So A1, 2, and B is equal to 1. Then you define a system. This system will be transfer function between B and A, between B, comma A. When you call this, the MATLAB will make a system, okay, a system transfer function. And for after you define that system, you can call the impulse function to get the impulse response of the system and the step function to get the step response of the system. So H is equal to, H is the impulse response, impulse what for what? For the system, comma t, that you define the time vector here, and the step system for the system, comma t. Okay, this is simulation from MATLAB. You will plot this together with the theoretical result you have here in part A. So in part A, first you will find the step response and the impulse response. Then you will plot the impulse response of the theoretical result with this impulse response. So you will plot them on the same graph. Okay, so they should be on top of each other. So you should make the theory result, and you will compare the theory result and the simulation result. Actually, that's what it means. They should be the same. And Also, the step response from the theory, you will plot it together simulation result. Okay, so you'll have two graphs, one for the impulse response, one for the step response. The impulse response graph having the theoretical and the simulation together, and the step response graph having the theoretical and the simulation together. Okay, so let's go to now to MATLAB, and let me show you. Here is the I have only done here the simulation because I want you to do it theoretical part and compare it. Here is how I define. Again, I clear all and B1, A12 system transfer function BA. When you call this, what will happen? I will show you when you define a system like that way. Let me. MATLAB will make a transfer function which we call h of s. H of s. H of s will be 1 over s plus 2. This is called Laplace transform. This one we will see it in chapter 5. Okay, we'll study it in chapter 5. For now, just only understand this, how to make a system. A system is equal to transfer function b comma a. Okay, the b vector and the a vector. Okay, then what I did here after that, h of the impulse system. So I find the impulse of the system and I put it in a vector h and I get the time vector. So if I do like this, it means it will give you the impulse h and the time vector. And then plot t, the impulse plot t versus h with black color here. And on the same graph, actually, I plot here the step response. How I call it? S of st is equal to step system. That means you'll get the step response. It will be in S vector, and also it will generate automatically time vector t. Then you plot t versus S on the same graph, and then you can make X label, Y label, and so on. So let me run this program. It is labs, the name of this is labs 3 v1. Okay, you can give it any name you like, labs 3 v1. And let's see the graph. So this is a graph, you see. As you see, the black color here is the impulse response, a decaying function. And here, the step response, okay, which is actually not decaying, growing function here, okay. Because the impulse is a derivative of the step response. That's why. Okay, this is the simulation. So you will plot on the same graph the impulse and the step response. Okay, the impulse response graph of the theory and the simulation separate, and the step response graph of the theory and the simulation. Okay, here only I showed you the simulation part. Okay, this is the first part of the exercise of lab 3. The second part of is we give an input to the system, to the same system, okay? And this input is now, in the second case, x of t e to the power of 5t ut. Then we will find, you have to find the theoretical result, okay, by giving this and by assuming initial condition 0, okay, using the concepts you studied in the theoretical lecture class, you will find the output y of t, okay, for the input e to the power of 5t ut, where the initial condition y of t is equal to 0. Then you have to find the homogeneous solution, the particular solution, and the complete solution for this input. Okay, that will be the theoretical result. That one you will plot it and compare it with the simulation result. Okay, how you do the simulation? Here b is equal to 1. Again, a is 1, 2. System transfer function b comma a. This is the time vector. This is x e to the power of 5t. Then you will call the function called LSIM, linear simulation. That means simulation of linear systems here. And then the output will be in y vector. So when you call this function, how MATLAB knows this function is already built in. So you will give the system for that function. How? Here from above, we already defined the system. And you give the input x, okay, and you give the time vector. So 3 things for this function, okay, the system, the input, and the time vector. So it can be any system now, okay, but for this particular case, this first order system. So it can be any input also, and for this particular case, the input is this one, and time, and you will get y. This will be your simulation result, and you will plot it together with the theoretical result you found, okay, and you compare the two results. And let's go to MATLAB. Now I did it already here, but you have to do it by yourself. And here is my function. Also, I found the theoretical result, and I have the theoretical result. And then on top of this, I have this LSIM function, y to LSIM system xt, and I plot the theoretical result y1 and the simulation result y2 using the LSIM function. Let's see how it looks like. Okay, so what you have to do, you have this, you define this b1 and everything, and you have to put the equation of the theory, and then you have this input, and you have to say y2 LSIM system x and t, okay, and then you plot the theory, and then hold on, and you plot the simulation y2 together, and you compare the two. Let me call this, this is for my case, it is lab3 v3. This is the name of the script file. So I run it. Now I am running this, this simulation. So let's see the result now. So now I get the output here. This is a result. Now I have the theory and the theory in black color and the simulation in red color, but I don't see the black color. Why? Because they fit. It's exactly the same. That's how you see the simulation is matching the theoretical result. So how you know, if we say legend, for example, insert legend, I should have two datas. One is for the black, one for the red color. Two datas. It's a little slow, the MATLAB in my laptop here. So I have here, you see, black data 1, which is the theory, and red is the simulation. Or what you will do, if I, for example, delete the red one, I just delete here the red one, red color. I see, delete it. I should, below I should get the black color. Delete. Yes, so below is the black color, which is exactly the theory is matching with the simulation result. Okay, this is the output of the system for the input x of t e to the power of 5t ut. Hope you understand this lab, and as usual, your lab should have all the theoretical works, the MATLAB simulation results, MATLAB codes, figures, and discussion. Discussion is very important because you need to explain your observation so that we know that you understand the concepts for the lab or the purpose of the project. Thank you for listening to this lab lecture.